This is a tutorial clip on buffers. Just to recap what buffers are, particularly acidic buffers we're going to focus on in this clip. So a buffer solution is one which resists changes in pH when small quantities of an acid or an alkali are added to it. So with an acidic buffer, it's made of a weak acid and a soluble salt of that acid, and that salt is called the conjugate salt. Now, because it's acidic at 298 Kelvin, the pH of the solution will be below 7. So how does a buffer work? Well, if it's an acidic buffer, you're going to have if you add a sodium hydroxide to the weak acid, then there'll be a neutralization reaction, so more of the salt would be formed, and then you'd have water as the byproduct. On the other hand, if you add hydrochloric acid to your acidic buffer, then the salt, sodium ethanoate, would react with the HCl, forming more of the weak acid, and then NaCl as the byproduct. So the pH would, in the second case, the pH would decrease slightly because you're adding HCl. You're making the weak acid, but only by a very, very small amount. This would be very different if we didn't have the buffer solution. If we added HCl to just water, then the pH of the solution would drop significantly. Now, on this side here, what I'm going to show you here is that we use Ka expression to calculate the pH of a buffer. So Ka equals H plus times by A minus over HA, where A minus is the concentration of the salt and HA is the concentration of the weak acid. We use this expression when we're calculating the pH of a weak acid earlier on. So now I'm going to talk to you about how we work out the pH of a buffer solution. So to start off with, we've got 0.1 molar sodium ethanoate, 0.15 molar ethanoic acid. How do you calculate the pH? Well, first we need the Ka, and the Ka will be given to you. You then write the expression Ka equals H plus times by the salt concentration times by the acid, divided by the acid concentration. So putting those numbers in, that's the salt concentration, that's the acid concentration. There's my expression. But what I've done here is I've rearranged the equation so that H plus equals Ka times by the acid concentration divided by the salt concentration gives 2.61 times 10 to the minus 5. And then to work out the pH, negative log of H plus 4.58 and to 2 decimal places. Now, how do we work out the pH of a buffer that's going to be made? Well, what's really important is that you have the weak acid must be in excess. This means that at the end of the reaction we have some of the salt being formed, the sodium ethanoate salt being formed, some of the ethanoic acid is also left over. So let's go through this calculation. We've got this volume, this concentration of sodium hydroxide, and we've got this volume and that concentration of the acid. I've worked out the moles of those there using N equals C times V. I then form an ICE table, so initial, change, end amount, and I've put the numbers of moles into the equation. Salt is 0 to start with because we're making a buffer, so there's no conjugate salt to start off with. And then the change amounts, well, we pick the lowest number of moles that's reacting. So NaOH is the lowest number of moles reacting, so it's minus 1 times 10 to the minus 3. The acid goes down by the same amount. The salt, on the other hand, a bit like the seesaw effect, so this side they go down in amounts, and the salt will go up. And it goes up by plus 1 times 10 to the minus 3. and so we have the end amount of moles calculated there. Water, we're not fussed about, doesn't really change very much. It doesn't really affect the pH at all. And then, like above, we put those values into the equation. Ka expression written there. Salt moles, acid moles, and then I've got the volume here. Now 0.11 is the total volume of solution, which is 100 cubic centimetres of acid, 10 cubic centimetres of sodium hydroxide, hence 0.11 dm cubed. However, they cancel, the volumes are the same, there's no need to calculate the concentration. We're showing that we're working out the concentration, but we do not need to calculate. The next step, as we did above, rearrange the equation so that the H plus is the subject. So Ka times by the acid divided by the salt concentration. We've seen that rearranged here. And then pH equals negative log of H plus, so 3.81 to 2 dP. This is the key equation for the buffer calculations. We eventually always work out the concentration of H plus equals the acid dissociation constant Ka multiplied by the concentration of the acid divided by the concentration of the salt. We do this in all 4 equations.